Thank you very much, and it's a great pleasure to speak here. And okay. So, can you hear me? Yeah. Today I'd like to talk about some problem which is famous not only the graph theory but also the computer science. And here is what I like to do in I can do everything except for the last. And I hope that everybody knows the graph. Is it okay not to define the graph? What is a graph? Well, okay, a little bit I will do that. And the next one is the minimax theorem. That I will do in the blackboard. Also, the two disjoint path problem. This is actually connected to the topology as well. So I like to talk about why it is connected to topology. Also, then disjoint path problem is actually the more general case of the two path problem. So I like to talk. Also, polynomial time algorithm. That's connected to the computer science. So if you are interested in them, I like to talk a little bit more. How many topologists are here working on? How many low dimensional topologists here? Not theory. Okay. You might know. Yeah, then I may speak a little bit on the topological graphs topology. The last question was the one that I was asked by, not my wife, by mother, actually. I don't really know how many people actually, how I don't know how to, in Japan it's called Toho Shinki, but is it? Honman Shinki, okay. And looks like, for your information, they are known, probably all Japanese people know them. Yeah, that's so famous. And my mother is a big fan. So she asked me how famous they are in the Korea. Maybe they are one of the celebrity, maybe the best celebrity in Korea, I think. I hope.
You should ask more
the students.
Yeah. 얼마나 유명하냐? 군대 갔다 오느라. Nobody knows. No, I think they are very famous.
They are famous, okay. So yeah, so I keep my word with my mother. That's just. And the whole point is that I'm stupid enough to ask this question to you in this talk. So feel free to ask any question or anything you want, because your question is not as stupid as this one. Okay. So feel free to stop the talk. Any question is good enough. Much better than the last one. So let me begin with one famous, okay, so let me check this. Okay. Let me begin with the graph. The graph is consists of the vertices. It's called, it looks like this, it's called the vertices. And plus the edges between two vertices. That's called graphs. And I hope that everybody can see what the graph is. Is it okay to go? Now, I want to talk about one very nice theorem in the graph theory, which is actually the origin of the so-called minimax formula. The theorem tells the following. Suppose I give you a graph. Then suppose you fix the 2 points, S and T. Then the following is actually equivalent. The first one is the number of the maximal paths. So I have S here and I have a T here in the graph. The first one tells you how many passes. Disjoint path means that these two paths doesn't touch. Is it okay? The path between 2 points. And the second one tells you that how many vertices are necessary to separate these two guys. And this one tells you that it's exactly the same. That's why it's called minimax. This is the minimum, and this is the max. And separate means this. Delete it, so yeah, you delete a vertex. Then that's, yes, no passes between that. Now, this theorem is actually important, not only the mathematical, so this theorem has a huge history, not only the mathematics, but also some political issue. I'm not going to tell you the deep one, but this actually comes from some military things. Imagine that this T is a Moscow. Imagine that S is Berlin in 1960s. Okay. So still Berlin is in the East Germany, was in East Germany. And the Berlin is somehow very close to the Western country. So it's very possible that the Germany or American troops could get Berlin back. So what Russia wants the following. They want for example, the troops, the fruits, or some other military things to send from Moscow to Berlin as much as possible, as many as possible. But because Berlin is so isolated, so they have to give help. So they have to send the troops, right? And what they are interested in is that what is the best way to send the troops or foods or whatever to Berlin, as many as possible. That's the Russian researchers are interested. And actually Russian government actually asked the researcher to invent the most efficient way to send from the Moscow to Berlin. Now, the US researchers and the German researchers are interested in the following. The best way to get the Berlin back is to cut the line between the Berlin and the Moscow. Basically, if you cut everything from the Berlin to Moscow, then Russia cannot send the troops. Then the German and the US people are interested in finding the most efficient way to separate the Berlin and Moscow. And it turns out not the same. That's this theorem tells. And in fact, that there is some interesting history that whenever the Russians send some troops, then they always found the US spy there. That makes sense because then the Russian government are very angry because maybe somebody is spying in Russia. But that's not true because basically both are the same. So Russians genius researcher invent the best way to send the troops as much as possible, as many as possible. And the US researchers are actually interested in how efficiently separate Berlin and Moscow. They turns out they're the same. So they always meet. And that's this theorem. So it turns out the Russians are maximizing that, and the US research is actually minimizing that. And in fact, traditionally, Russian research is very strong to send it's called the flow, right? And what's the value? So they want to send the flow as much as possible. They are very strong on this area. And US researchers, in fact, German researchers, very strong at cut. That is just to separate, how you efficiently separate. And it turns out those two researchers actually intersect, and basically the solution is the same. And that is this theorem. And this is one, so they intersect both the cut and the flow, path business. And that's really nice. And this is one of the best known results in the graph theory. And starting with this, people are interested in such a path business or cut business. Now what I'm going to talk about is actually cross-probe, but a little bit different. In this case, you only fix 2 points, Moscow and Berlin. But what I want is not only 2 points, but also simultaneously many points. And the point is that I have so it's called terminal. That's the point I specified. I also have another point. And I want to send the path or send the information to the specified one. So from T1, you have to send the information to S1, not other guys. From T2, you have to send the information to S2. And somehow the point is that they don't want to intersect. There are many reasons, like, when you're sending the information, which is very important, they don't want to cross, and that could be confused. What they want is that just right now, not only the maximizing that, but just send one information to the specified one, like Berlin to Moscow and Seoul to New York and Tokyo and Madrid, but simultaneously. Let me just formulate more mathematical fashion, but that's an algorithmical fashion. But the problem is that suppose I give you a graph. So you can imagine that the graph is just the network, road network, whatever. And I specify the point, S1 to T1, and T1 to S1 to SK, and T1 to TK. Then what I want to ask you is that, is it possible to join 2 points, specify 2 points? I'm not asking you that the maximal one, just one is enough. Only I want to send the important information. Well, that is also considered by the many military reasons, because you want to send many important information as much as possible simultaneously. But it turns out the Russian people and also US people as well they recognize that this is really a hard problem. And they couldn't solve that. And it turns out in the 1970s, this is one of the most well-known NP hard problem. Well, okay, NP complete problem. Let me just, I'm not sure how many people know the NP hard or NP complete. Probably not so many, right? So let me just give you one. Okay, so how many people know PNP? Question. Okay, half of people. So I'm not going to define as very formal define, but I'm going to give you one. I hope it is good intuition. If I need to define an NP or NP complete, I need to define P as well. And P and NP is not really the separate one. It's actually the one is contained the other. In fact, P is contained NP. And P means the following. Just simplify the question that I only consider the graph. Suppose I give you a graph. And the graph consists of, as I said, the vertices and edges. If I can solve the problem in polynomial steps in terms of the input, that means the number of vertices, number of edges. So then there's something like C, or C1, C2, and the C1 and C2 are completely different, completely independent of the graph. That's problems are called P, solvable with P. Now in P, that's actually not so easy to define. But here I give you the intuition. And some best mathematicians say that P is the following. P is that you you set up a conjecture, let's say mathematics, and then the P is time constraints, or the time period, how long it takes to solve the conjecture plus write up a paper. Okay? The NP is you referee the paper. How long it takes to referee the paper. So NP means already the solution are there. The solutions are there, and what it asks is how long does it take to check the solution. So that's same as it's not really the same as the referee, because sometimes there's a mistake. But assuming that there's no mistake, how long does it take to solve to check the detail, check the correctness? And basically, many mathematicians believe that those sides should be completely different, right? Imagine that Fermat-Russell, it took a human 100 years to solve. But to referee, maybe just a few months. Not just a few months, I don't know. Poincare conjecture, it took a few 100 years. And check maybe at the most half a year or something. So that's somehow the intuition. I'm not saying that this is a good definition, but that's somehow the intuition. Okay. Now, the problem called NP complete is basically somehow the most farthest from P. Well, I mean, some people believe this class and this class, the P and NP is actually equal, but many people are not. Basically, the expert, none of the experts believe that. It should be basically the completely different family. And NP complete problem is basically the hardest problem in the class of NP. And also, it's sometimes, well, okay. So that means that if you really believe P and P, what you really need is prove the given polynomial time algorithm to solve any NP complete problem. That's enough to prove P and P. But nobody believes that actually. Now, this question, disjoint path problem, so the concept of P and P is invented sometime in the 1970s. And this question is one of the original NP complete problem. So it's discussed from 1970s to 60s, and people realize that this is really the hard problem. Now, I'm saying that if K is as a part of input, it means the following. Okay, so K is the number of the terms I'm giving. Okay. And later, there is the very big result in graphs, in the graph algorithm and theoretical computer science, that if K is as a part of the input, then it is solvable. It means that just imagine that K is just a constant. Then it is solvable. Well, don't worry about that. I will give you more details afterwards. So. Actually, if I say disjoint, there are actually two meanings. Sometimes that disjoint means vertex disjoint. So the vertex is actually disjoint means that two paths is something like this. And edge disjoint means that it's okay to intersect at the vertex, but it's not allowed to intersect at the edges. This is edges. So this is, do I have a color chalk? Okay, it's fine. So imagine that this is one path, and this is the other path. This is called a disjoint because they share vertices, but they don't share the edges. Does it make sense? The vertex disjoint, the edge disjoint. Okay.
That's disjoint or?
If I say the disjoint, then there are two kinds. Vertex disjoint means that the vertices are completely different.
Even vertices.
Yeah. So in most of the case, I will discuss vertex disjoint. Okay. Let me just. This question is interesting. So this question was raised from the algorithmic people because I told you that they are interested somehow in the mutabilism. But in 1970s, the mathematicians are also interested. Let me give you the mathematical home. And the mathematicians are actually interested in the following, right? Basically, when is this question always true? Let me just give the mathematical form. It's called the graph is K-linked so suppose I give you a graph, and you can specify any K vertices, S1 to Sk, and T1 to Tk. And the K-linked graph means that in the previous case, the answer is always yes. No matter how you choose S1 to Sk and T1 to Tk. No matter how you choose that, the answer is always yes. It doesn't matter which one, but in any case it is true. This kind of graph is called K-linked. And that looks like the best measure is its connectivity. That's actually connected to the first one. Now I'm saying that graph is L-connected if, yes?
So can I have all the vertices the same? S1, S2, Sk, they're all the same vertex?
It could, yes, you could.
Yeah.
Yes. It doesn't matter different or the same. But the whole point is that no matter how you choose, it must be.
So it means K-linked, it means I must, from any given vertex, have K disjoint cycles that come back to the same.
Yes. Yeah. You mean S1, T1 same or something? Then that's a cycle. Yes. Okay. So the measure that seems to be very relevant is called connectivity. Now it's called L-connected if for any two vertices S and T. So just imagine the example I gave you at the beginning on top. S and T, there are L disjoint paths between two of them. That's called L-connected graph. And it seems that if you take any 2 points, if there are many disjoint paths for any 2 points, then presumably you may be able to get something like the K-linked graph. That's a mathematician's prediction, and that's one of the hot area in the graph theory, because it's actually a huge history. Let me just write some history about that. And the best measure is that what's the connectivity depending on K force to the graph so that the graph is K-linked. And this has a true history that it started with German's great graph theorist called Mahler. He proved that upper bound is actually 2 to the k. And this result was best. No one could beat this part, and significant improvement was done by Robertson Seymour in the graphite theory in 1995. And they proved that f of k is actually k square root of k. That's a funny number, but. Now, soon after that, Borbas and his student Thomson proved that 1996 proved that f of k should be 22k. That's also the Borbas is so let me just mention that Borbas is one of the famous mathematicians. He's a supervisor of the Tim Gowers. Now, then that was open for a while. Then, okay, let me just skip that. You might ask, what's the lower bound? The lower bound was also the conjecture by KAIST and Thomson, which is one of the important graph theorists, one of the big graph theorists. It is actually 2k plus 2. That's the lower bound. I'm going to give you a graph a little bit later. This makes sense when I give you the two case. And the current best bound is 10k. From here to 10k, just a couple years ago. But still big gaps between two of them. So that is one. Sorry, so to skip that. Now, this is still far from best possible, but we can do something for 2. The 2 case is actually interesting in the sense that it is connected topology and Jordan-Kroll-Skarp theorem, I should say. Now, the reason why it is connected is the following. Let me say, just delete this. This is proved by Paul Seymour and KAIST and Thomson, both the big guy, the graph theory. They characterize the following. When k equal 2, and suppose graph is 4 connected, then the disjoint path theorem holds, or the obstruction is the following. The next picture is much easier, maybe. So you have a disk here, and the graph is completely embedded. So you imagine that this is plane and planar graph. And here you have a one pairable terminal S1 and T1. Here you have a two terminal S2 and T2. I claim that this is obstruction. The reason is that if you need to connect S1 to T1, right, that separates S2 and T2 in the plane. If you assume the Jordan-Kroll-Skarp theorem, then these arc like this in the outside, and this is the Kroll-Skarp, and the T2 and S2 different side you cannot connect. That's the topology comes in. And I should mention that in the previous slide, Carsten Thomason, one of the guy who proved this, actually he gave a new proof of the Jordan closed curve theorem using this fact, using graph interpreted graph theory, and that was actually just a 2-page proof, and it's appeared in American Math Monthly, I think. And this result was nice because not only the mathematical reason, but also the algorithmic aspect. This nice characterization, right? If you give me this one, it's easy to confirm that this doesn't contain the 2 disjoint paths. This is called sometimes this kind of characterization called nice characterization, because if you give me this example, then I can confirm, oh, you are right that it doesn't exist. And also, this proof also implies that the polynomial time algorithm times it's only the number of vertices times the number of edges. Now the problem is that this is nice, but we deadlocked. If you go further, then no nice characterization is known. Okay. Now let me come back to the previous issue. I said that the lower bound is 2k plus 2. That comes from the same graph. You have this structure, but I add a S3T3 to SKTK. Vertices here, and join everything. So those guys, everybody is adjacent to here. The whole point is that if you need to connect S1, T1, S2, and T2, they have to use the planar part. Because if it is disjoint, so this guy is not allowed to use any of them. So it's come back to the planar graph. And if you join everything, then it's going to be 2k minus 3 connected graph. 2k plus 1 connected graph. So this is kind of mathematically known thing. Is there any question? I'm going to the second half. It's okay to go ahead. Okay. Now, let me just. Oh, okay. So DP means disjoint path problem. It's just a short. We have looked at. So the first issue, just ignore. I don't really know anything. I'm actually not the practical people, so I don't know anything. So don't ask me. So far, we looked at the 2-path case. That's connected to planarity and the Jordan closed curve theorem. And then if we increase the connectivity, then you can do something, like I did there. Now I'm going to switch to a little bit algorithmic part. But don't worry about this kind of stuff is not really computer science. This is really mathematics. I mean, you know, I don't really know anything about the first one. That's okay. You can just work on that. This is mathematics. But the area it's called combinatorial optimization, and theoretical computer science. That's close to the, sometimes it's close to the operation research, sometimes also connected to combinatorics and discrete math, and also computer science as well. This concept, this problem is one of the most important problems. I'm going to give you a little bit more about that. Also, there is another the branch of graph theory. It's called algorithmic graph theory. This is a kind of the area that solves a graph theoretical problem in polynomial time. And this disjoint path problem is one of the most important things. Also, that I should mention that this problem becomes important because of it's the famous project called Robertson-Seymour theory. I'm going to give you the last one. The reason why this is important is that Robertson-Seymour gives a huge result. They prove that if you fix a k, so think about k as a constant, then you can decide this problem in polynomial time, actually the cubic order of the number of vertices. Now, fixed k means the following. Their time complexity, so how long does it take to solve using their algorithm? Their algorithm can solve the problem like this. In terms of this time, but because as I said, the k is fixed, so it's okay how big this function is. In fact, in their algorithm, actually, how big it is, I cannot actually write it in this blackboard, because that's too big. Basically, it's bigger than that. The tower is also bigger than k. Right? But still polynomial, because if you fix a k, if you put the k equal 3, 4, 5, 10, this is constant in terms of mathematics. The computer scientists say, oh, that's nothing, because it is never possible to implement it. Also, there's another thing I have to say. Proof needs actually more than 300 pages. It really needs whole the graph minor theory. That's not so easy to understand. And and also Bruce Reed, one of the experts, and I are able to improve the time complexity. That's not trivial in a sense, because we are using whole the 300 pages proof. So this gives a huge impact in the algorithm, but unfortunately nobody can implement it.
So the constant is still big even for the improvement?
Fit improvement? Oh, this one?
Even for the improvement, the constant is still...
It's still larger, and even larger, unfortunately. And so I'd like to mention a little bit about topology. So their framework works not only disjoint path problem, but also the following.
So these problems are in standard graphs, right?
This one? No. It's any graph. Any graph, you can do that. In the planar graph case, it's a bit better, but I'm going to talk a little bit about the connection to topology. Their framework works not only the disjoint path problem, but also the nice problem in the topology. Here is a problem that I like to talk about. Do you know the link? And do you know the knot? The knot is this. Right? And the link is, can I write the link here?
Your second picture was linked.
It really?
You have a small link.
Oh, yeah. That's great. That's great. So this is one of the ring, and this small, tiny one is this ring. Yeah. Now, here is my question. Suppose I give you a graph. Your task is to embed in a 3 space so that there is no link. That's one. That's the first question. Or there is no link, no knot. Can you embed it? How do you?
Embedding means you use just the intersecting point with a separate.
Yes. So in a sense, it's not the general position. And the graph miner algorithm actually say that yes, you can do that in cubic time. And quite recently, I have invented that with Stefan Kruse and Boy Mohan that if there is, I can actually construct a linkless embedding like this. This tiny one. No, sorry. This is not linkless. There is a link. So if there is embedding without such a thing, I can construct that in quadratic time. But the big open question is, can you do that knotless? So the Robertson Seymour framework works to give a decision problem, yes or no. But their algorithm is not enough to prove that there is actually the embedding, to construct the embedding.
Is it possible to make this graph?
Yes.
I mean, if you say embed, sometimes you can make it link,
Yes.
or sometimes you can make it not.
Yes.
So, is there a graph which
Yes.
cannot be embedded as not this or not embedded?
Yes.
But not only can be embedded in a link. And the other
Yes. So that graph is called. Some of them are known.
the link is
That's right. So it's graph called case 6, meaning that 6 vertices and the edges stick to every pair. So all the possible edges. And John Conway proved that this graph has no linkless embedding. So no matter how we embed it, John Conway, the famous John Conway, proved that that this graph, no matter how you embed it, you have to have a link. Yes?
So you have two disjoint cycles that so should that be trivial now, or?
So this case is that the input is only graph.
Yeah, okay.
Then I construct the embedding.
No, my question is about what does linkless mean?
So linkless means that, yes, so yeah, that's right. So you pick up any 2 disjoint cycle,
Okay.
then there is no link.
I mean, they should look like this.
Yes, exactly.
So in particular, this means it is knotless.
Yes,
Okay.
yes. But maybe, this may happen, right? So that is one cycle, and the other cycle is up and down, like this. That's still linkless.
But not this, right?
Not there, that's right. That's right, exactly. Well, the two of them, both are actually going through the inside. But it's knowing what, so we can do the linkless embedding, but we cannot do the knotless. I don't know how to do that. That seems to be hard. And plus, okay, let me just give 1 minute for the big question.
How can you tell whether there exists or not?
So the linkless case, it's called forbidden minor. If you know the planar graph, Kwiatkowski graph characterization, it's the graph doesn't contain K5 or K33 as a minor than planar graph. The linkless case also, it's not the K6 of the Peterson graph. Maybe I can write correctly, I hope. This way. And some other 4, 5 maybe. If these graphs are not the minor, then you can, it must exist. Also, the problem for the knotless embedding is that we don't really know what which graph exactly this kind of forbidden one. We know that.
You don't know the minors. You don't know the forbidden minors.
We don't know. We know the upper bound. So forbidden minor has to be at most 100 vertices or something.
Okay. How many?
What? Excuse me?
How many vertices?
100. So in terms of the algorithm, you can check, 100 vertices. Can you so eliminate all the graphs up to 100 vertices and check all the possibility if you can embed in the knotless. Then you pick up all the forbidden minor. You can test that. But mathematically, we don't know which graphs can do that. Yes?
So what it means is these linkless and knotless, they have list of forbidden minors.
Yes. So the big graph minor theorem tells you that if this kind of the heredity, so closed heredity property must have a finite number of the forbidden minors. So also in the knotless case, the knotless case, we know that there's really the upper bound, 100 vertices.
How do you know the upper bound?
We can prove that. Well, how do I say? It essentially comes from the. So basically, it says following: if the graph has big enough, right? And also, I should tell that K7, 7 vertices, and the complete graph. The edges add everything. Though this graph does not contain the knotless embedding. And if if you exclude case, minors, and one of the forbidden minors. So this is one of the forbidden minor, and once you exclude this, then structure is kind of the restrictive. So we can pin down to the small number of vertices. But it doesn't tell you which graph. So it doesn't tell you which graph is really the forbidden minor. And at the moment, we have more than 100. So it's probably not feasible to list up everything because we already have 100. And you might expect that you can do the computer search, but it's too big. If you go beyond 20 vertices, you cannot do anything, unfortunately. Computer is not enough right now. Okay, so that's a topology thing. Let me skip that. And then finally, I like to talk about. Okay, so do you have some question? I maybe stop that. And the last part is really the computers, more like theoretical computer science stuff. So finally, I'd like to talk about approximation. That's a trend of the computer science. As I said, that the disjoint path problem is NP hard, NP complete. So what's the theoretical computer science? So also there's another problem which is close to the disjoint path, which means the following. Suppose I give you the term is S1 to Sk and T1 to Tk. But k is not fixed. It could be linearly many. Okay. Then the question is, how many pairs can you match in the disjoint path? That your task is take the disjoint path with the specified end as many as possible. Does it make sense? So the optimal will be the path connect S1 T1 and the S3 T3 and the S100 to T100, whatever. But your task is to find the disjoint path as many as possible. Okay. Does it make sense? And this problem is still NP hard. Okay, so sorry, the NP complete problem. Now, what the computer scientist is interested in is the approximation. Okay. The approximation is the following. First of all, let's fix opt. Opt means optimal solution. We don't really know what is optimal, but there is optimal, right? We don't really know how to compute that, but there is optimal. Now, the C approximation in this case is that you give it the polynomial time algorithm, okay, that connects at least 1 over C opt number of the passes. So again, my question was maximize the number of paths pairing the S1 to Tk, but that's an NP hard problem, NP complete problem. So your task is to get the maximum number of paths as many as possible, but your algorithm guaranteed 1 over 6 optimal. Does it make sense? The reason why this kind of stuff we're interested in TCS is that the theoretical computer science is that they really want to see what's the border between the P and NP. Okay, so the problem, disjoint path problem, is maximizing disjoint path problem is NP complete, but what is possible? So this is NP complete area, and how can you maximizing the area of P to up so that this part is a 1 over C approximation algorithm, but still polynomial time. The point is that you really have to get the polynomial time algorithm, P, class P, but your algorithm should be as close as optimal. What is the best way to do that? Or what you can hope? You can hope for the 1 over C. Does it make sense? But it's, yes.
Higher one step above. You said NP, it starts as NP hard, but is it?
Sorry, yes, NP complete problem.
Is it also NP complete?
Yes, NP complete. To maximize that.
Shouldn't it be maybe in, I don't know, pi 2 or
No, because this is just maximizing the number. So well, okay. I think I know what you want to ask. The 5. Well, you know, if you want to enumerate everything and then test whatever, right? If you need enumerations, it's going to be 5 or something.
So if you decide whether some k is the maximum, then
Yes.
basically you have to say that this is possible and everything above it
Yes.
is not
Yes.
possible.
Yes.
This is, I think, not in NP. Then you have, there exists such that for every. And you have this kind of condition to define it, which
Yeah. Okay. You're right. So okay, yes. Yes.
it's in the next.
Yes. 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 Okay. Okay. Thank you. Yeah. 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 Okay. Yeah, but for simplicity, yeah, I did that. So sorry for that. But okay. So let me just continue that to finish my talk because it's quite close to the time. It's still somehow annoying that so far we are only interested in the undirected case, but directed case meaning that so each edge has a direction. This case is really horrible. You cannot approximate m square root m. M is the number of edges, the arcs, number of edges. So it means that C is m1/2. And I've said it's hard to approximate, meaning that if you break, if you can get more than, if we could prove that this is smaller than 1/2m, that proves PNP. And for undirected case, well, the things we discuss is that best term is log, this one, log. C is log 1/2n. Yes, square root. Let me just skip that. Yeah, so forget about, so what we can do is at most this. So in previous slide, I gave you the lower band. Meaning that you cannot approximate it better than that. But the upper band is also somehow horrible. And the directed case, it's same as that. And the undirected case, it's somehow the current no upper band is square root n. That's horrible in the sense that it's big gap into that. We know that if C is below that, it's going to be hard, NP hard. But currently what we know is up to this one. And this is actually the very hard problem to sharpen in computer science. And maybe somehow speak that. And what we can do is let me just, so because I'm running out of time, but let me just give one result I have, because this is in a sense nice and generalizing the John Kleinberg result. That's I like. So you probably know that Kleinberg is a Nobel Prize winner last time. John Kleinberg gives he gave a square log n approximation algorithm for Eulerian planar graph. I'm not going to define that because it's running time, but just say that this family of the graph. Then with my student, we finally give log n. That's a bit better. And as I noted that the smaller is better. Okay. Okay, so I'm running out of time, but let me just give some open question that the big open question is the first one. That's probably everybody wants to prove. For this disjoint path problem, as I said that we know that you cannot beat this bound. Because if you beat that, it's going to be NP, it's going to prove PNP. But currently, we only know this bound. The computer scientists believe that this should be close to that. There should be polylog n approximation. And this will be the huge result in this area because so many people are working on that, and even this approximation to that will be huge. This makes a little bit only a small difference, but that is also huge and makes a huge journal, maybe makes the best journal in the field of computer science. So I think I'm running out of time, and the last thing I like to do is show my cat. Thank you very much for your attention.